Area. What does area have to do with calculus? Well, we're going to go back to geometry here for just a little bit. We're going to talk about what we know about area from our work in geometry in high school, and then we're going to bring that knowledge and add to it what we need to know about area when it comes to calculus. So remember when we had all these different types of polygons in geometry, we had rectangles and parallelograms, triangles, pentagons, so forth. We learned formulas. This was length times width if we wanted the area of that. The area here was 1/2 base times height, and then there was, something that had to do with this length from the center vertically down, and that was called the apothem, and all that kind of stuff we had to learn in geometry. And then if we had a complicated area or space that we needed to find the area of, it was easier for us to break it down into known pieces where we could find the area of a triangle and then add it to the area of a rectangle and then add it to the area of our pentagon. And if we had, let's call this area 1 and this was area 2 and this is area 3, then if we wanted the area of the whole thing, we understood that we just added those 3 areas together and that would give us the area of the whole thing. So I think that's knowledge that we probably bring with us from our geometry classes. When we were to find areas of some sort of geometric figure that we did not have a formula for, things got a little more complicated. So let's talk about the exact definition of area. Because we could have, if this is the center, and then we might find this distance, or we might find half of the area and get twice that. But if we have a curved or circular boundary, something that's not a regular, these were regular polygons, anything that had a linear side, even if it was leaning on its side, we still had a formula where we could find the area of that linear figure. Well, as soon as curves or circular boundaries come into play, we had an issue in geometry. As a matter of fact, we didn't even really look at anything beyond the area of a circle. So let's recall that in defining a tangent, we first approximated the slope of the tangent line by slopes of secant lines. And then we took the limit of all those approximations. We had, some curve in the plane, and we had the tangent line. First we had the secant line through 2 points, and then we found another secant line and another secant line and another secant line, leaving 1 point stationary. And as we took those points closer and closer and closer to where we just basically had 1 point lying in the plane along atop of the other, we talked about taking the limit of the difference in the y's over the difference in the x's. We're going to do much the same thing in the area context. When we attempt to find the area under a curve, we are going to use limits and we are going to use approximations. We're going to start with approximations, and then we'll learn something called the fundamental theorem of calculus that will give us an exact answer. But let's say I wanted to find the area here of this dark portion in the plane that's trapped under some function y equals f of x. There's nothing linear about it except this one side right here and this underside right there. But this part right here is all curvy. So how do we find the area of something where we don't have anything that we can carry forward from geometry with us? Let me pull this up so we can kind of see what's going on here with everything. Okay, so let's say we want to find the area that is trapped in the plane underneath the function y equals x squared. This area I'm kind of attempting very poorly to shade in. And we want the area between the x values of 0 and 1, and we want it trapped under the curve and the horizontal x-axis. So let's say that this area is important to us and we want to find what that area is. So when we have a figure we can't easily use a formula to find the area, we usually broke that figure up into smaller figures that we did know how to find the area of. And so we find we can do this with curves as well as any kind of geometric figure with straight sides. And one way that we do it, the most common way, is we find a geometric figure that we like to take the area of. We know how to take the area of a rectangle, and we're going to use that to approximate the area under the curve. And all I've done here is I've drawn 5 rectangles. There's one rectangle whose width starts here and stops here, and its height is 0. And I started there on my curve and went to the right and said there's the height of a second rectangle, and I went the same distance, the same width over for each of my rectangles. There's the third rectangle, here's the fourth rectangle, and here's the fifth rectangle. Well, this question said, would this be a good approximation for the area under the curve? Well, we're leaving some area out. This is most definitely an under approximation because none of that is going to be included when I add up the areas of these 1, 2, 3, 4, 5 rectangles. But this would be a good ballpark. This is going to give me an idea. It's not exact. It's most definitely an approximation. But it's a good ballpark approximation for what the area trapped in the plane would be. There's more area, sorry, that'll be left out. All right, so let's say that instead of putting the left upper corner of my rectangles on the curve and going horizontally over the same width, let's say I put the right upper corners on my curve. And all of the widths from here to here and from here to here, all 5 widths are the same. I wouldn't have to do it that way, but let's just say that I did. And that the upper right-hand corner of all of my rectangles are lying on the curve. And then I just go over my width and go vertically, can't do it very well, straight down till I hit my horizontal axis. Well, again, this is going to be an approximation, but is it going to be a good approximation? Well, my argument is it's going to be an over approximation for sure, because all of this area is not actually trapped under the curve. So this is going to be an over approximation, but it's still a good ballpark. Okay? So we get the idea that we're going to use areas of rectangles, and we're going to add all of those areas up. Here we have area 1, there's area 2, there's area 3, area 4, and area 5. So the actual area would be approximated by the sum of the areas of all of these rectangles. Not a perfect area, exact area, but a good ballpark approximation of what the area is trapped in the plane. So we can easily find the areas of rectangles, but we're underestimating the area of the curve here. On the last example here, we're overestimating the area for sure. So how can we fix it? Well, we can fix it if we had more rectangles. As you can see in this example, the more rectangles we have, the better the approximation. So here are 5 rectangles. Here are many more. I believe this is 50 rectangles. I can't remember how I did that. It's been too many years ago. But this is many more than 5 rectangles. And we're still, you can see these little areas here and here and here and here. We're still underestimating the area trapped in the plane between this curve, the horizontal axis, x equals 0 and x equals 1. But if we continued increasing the number of rectangles, let's say we had n rectangles that we place under the curve until we get extremely close to the actual value of the area under the curve. And this is how we are going to approximate the area under the curve. We can have a finite number of rectangles, or we can have the number n, and we can take n to infinity. Anybody see a limit? And if we take n to infinity, we'll have the exact area trapped in the plane. So here is using left endpoints. We go to the curve and we find what our widths are. Here our widths are all the same, but they're all real tiny. But they're all the same for each rectangle. And so we find our heights by going a distance of one width over. And let's say we're doing left endpoints on our rectangles. Then our upper left corner lies on the curve, right? And that's where the height of all of our rectangles come from. So our heights would come from left endpoints, and our widths would be taking this right endpoint minus the left endpoint divided by our widths, or our change in x, which is going to be our widths of all of our rectangles, would be the right endpoint minus the left endpoint divided by the number of rectangles. And that would give us a standard width for all of our rectangles. All right, we could do the same thing by putting our right endpoints on the curve. Our widths would be a standard width, and we would put the upper right corners of our rectangles. It would still be an overestimation because the right endpoints are give us more area, even though there are a lot of them. It's still slightly an overestimation of the area. So if we took the number of rectangles to infinity, in other words, if we took the limit as n approaches infinity, the number of rectangles of that area, or of all those areas, we would get the exact area in the plane. And that's pretty handy. All right, so here was our function. Our function was y equals x squared. We could underestimate with left endpoints in this case, or overestimate with right endpoints in this case, the area under the curve. So it turns out that the area trapped between the curve and the horizontal axis has a really big meaning in calculus, and we'll develop that here in a while. First, we want to just talk about how we are going to approximate the area trapped in the plane. Then we'll talk about what the area actually means to us. So if we used a fixed number of rectangles to approximate area in the plane, we'll do some examples. Probably the best way to figure out what we're doing here. So here we have the same function, but instead of going from x equals 0 to x equals 1, we're going from x equals 0 to x equals 2. We're using 5 rectangles. It says approximate, and it will be an approximation. Approximate the area in the plane between y equals x squared and the horizontal axis. Here's the horizontal axis. It comes on right here. From x equals 0 to x equals 2 using 5 rectangles whose left upper corners lie on the curve. And here we have it drawn for us. The left upper corner there is on the curve. That corner's on the curve. There's a corner on the curve. There's one. And there's one. So I'm going to have 5 different areas. I'm going to have area 1, area 2, area 3, area 4, and area 5. And I can see that all of those widths are the same. From 0 to 2, all of those widths are the same. So I'm going to find the widths of my rectangles. Area 1 is going to be width times, we'll say, height. I know for rectangles we're used to length times width, but since all of our rectangles are pretty much going to be turned up on end, let's talk about width times height, can we? So the width is going to be, and it's going to be the same for all of them, area 2, area 3, area 4, and area 5. All of them are going to have the same width. So let's see if we can figure out what that is. So I need my right endpoint, here are my widths, minus my left endpoint, divided by the number of rectangles I have. So all of my widths on each one of those rectangles is 2/5. So if I'm going to find the area of each rectangle, all of my widths are the same. So let's just go ahead and fill that out, and then we'll figure out how we find those heights. All right, so all of them have a width of 2/5. Now let's find the heights. Let me come back up here and kind of clean this up a little bit so we can see what's going on.